Example number 8, on implicit differentiation, determine the equation of a tangent drawn to the circle x squared plus y squared is equals to 16 at a point when x is equals to 2. Now, if you look at this case, when you want the equation of a tangent, you know that the derivative of a curve at a point is actually the gradient of the tangent at that point, isn't it? So it is like they're telling you, the first thing you need to know is the derivative of this curve, isn't it? You need the derivative of the curve, at the same time you need one known point, isn't it? What is the one known point before we go to the derivative? The point is supposed to be in the form xy, isn't it? You've already been given x to be 2. You've already been given x to be. So what is y when x is 2, isn't it? Meaning where there is x you put 2, isn't it? So 2 squared is 4. So you get 4 plus y squared is equals to 16. Taking 4 the other side, you remain with y squared is equals to 12. Are we together? Y squared is equals to 12. So what is y? Square root of 12. You get the answer to be plus or minus 3.4, meaning the first one is 2, 3.46, and the next point is 2, negative 3.4, meaning when x is 2, y has 2 values. Are you seeing that? Are we together? Are we together? Meaning in this circle, we want, if this is the circle is like this, if the point x2 is here. If the point x2 is here, meaning one of the y is here, the one tangent is passing like that. When x is 2, the other tangent is passing like this. The y is positive, y is negative. Negative 3.46, positive 3.46. So there are 2 tangent lines. Are you seeing that? Are we together? Meaning in this circle, we are dealing with the 2 different tangent lines, isn't it? So you get the equation of the first tangent line and you get the equation of the second tangent line, isn't it? Are we together? And you know what? The derivative of the curve is actually the gradient of the tangent. Is that okay? The derivative of the curve is the gradient of the tangent. So here you've been given x squared plus y squared to be equals to 16. What do? For you to get the derivative of the curve, meaning you are differentiating with respect to x, isn't it? So for you to differentiate with respect to x, that is implicit differentiation, isn't it? Meaning we differentiate x squared with respect to x, then plus we differentiate y squared with respect to x, isn't it? Then we differentiate 16 with respect to x. That is implicit differentiation because we want the derivative dy over dx. Now having done that, you apply the rule where it applies, you don't apply it where it doesn't apply. So here x squared, if you differentiate x squared, you get 2. Then you are differentiating an x variable with respect to x. You remain with the x over the x. That is silent, isn't it? You go to the next one, plus, when you differentiate y squared, you get 2y. Then you are differentiating a y variable with respect to x. You remain with dy over, you are done. To be equals to 0. Anytime you are differentiating a constant, you get 0. Anytime you are differentiating a constant, whether the constant is 0, the constant is a number, or a constant is an unknown, some unknown value. Now from there, we want the derivative dy over dx. We make it the subject of the formula, isn't it? So taking 2x the other side of the equation, we have 2y dy over dx is equivalent to negative 2x, isn't it? So you divide both sides of the equation by 2y. So having divided both sides of the equation by 2y, you end up with dy over dx to be negative x over, because 2 will cancel out with the 2. Negative x over y. Now, you want the gradient, you want the equation of a tangent at this point and at this point. Those are 2 different tangents, isn't it? So let us start with the first equation at this point, what is the derivative of the curve at this point, isn't it? So at this point, the derivative of the curve dy over dx is negative x over y, meaning negative, you substitute the value of x at this point, you substitute the value of y at this point, isn't it? Are we together? Meaning it is negative 2 over 3.46. So what is the derivative at this point? Give me the derivative at that point. Negative x over y, but x is 2, y is 3.46, isn't it? Are we together? Are we together? Good. Negative 0.5? 78. Negative 0.58, isn't it? At this point, so the gradient of the curve is negative x over y. So what will be that derivative at the point when x is 2 and y is 3.646, isn't it? Meaning where there is x you put 2, where there is y you put 3.46. Then you are able to get the derivative at that point, isn't it? So the derivative of a curve at a point is actually the gradient of the tangent at that point, isn't it? So when you want the equation of a tangent, then you should be able to know that the derivative of the curve dy over dx is the gradient of the tangent, isn't it? So what is the gradient of the tangent? Change in y over change in. So change in y is y minus y value, which is 3.46 over x minus x value, which is x minus 2, to be equivalent to the gradient of the tangent, which is the derivative of the curve at that given point. So if you simplify that given equation to be in the form of y is equals to mx plus c, then you end up with y is equals to negative 0.58x. Do the calculation and give me that value. Negative 2 times negative 0.58. 1.6. Then negative 3.46 going on the other side of the equation you add, isn't it? Isn't it? Are we together? What do you get? Plus 3 point. I got the answer to be 4.62. This is positive, my friend. I'm not teaching algebra, I'm teaching calculus. Algebra is something you know. You get this plus 4.62. Isn't it? Good. So you've actually determined the equation of the tangent. So you see, can you use the same method to determine the equation of this second tangent? Because there are two tangents, isn't it? So I've determined the equation of the first tangent. Can you now determine the equation of this second tangent? And can you now determine the equation of the normal at a point when x is 2? Are we together? Good.